Unit 8, Change is the Only Constant. You can access this review and this video at srhschem.wikispaces.com or on YouTube channel LaFell Labs. First question asks us to explain the relationship between temperature and rate of reaction, and then to include a graph that shows this relationship. So as temperature increases, those particles are going to start to move faster as they're gaining kinetic energy. This is going to cause more collisions to occur between reactant molecules, and as we get more collisions, that's more chances for the reaction to happen, so we'll increase the rate of reaction. So here I've got two reactions, and I've got my reactants, and one is at low temperature. So these particles are going to move very slowly compared to my other particles, which are at a higher temperature. So my higher temperature particles are moving faster, so just because of the fact that they're moving around so much, they're more likely to collide with each other. This will increase the rate of reaction. So we see between temperature and reaction rate a direct relationship. As temperature increases, reaction rate increases. Now, of course, there'll always be exceptions to every rule. This is just in general for a reaction. Certain reactions might actually slow down as we get to very high temperatures, but in general, direct relationship. As temperature increases, rate of reaction increases. So the next question, how will each of the following affect rate of reaction? So we talked about temperature. In general, a higher temperature means faster motion of particles, which is going to cause more collisions and speed up the rate of reaction. If a reaction is exothermic, however, that reaction is trying to get rid of heat. So if I increase the temperature, it might make it more difficult to release heat, and that can cause the reaction to slow down. If I decrease the surface area, basically I'm making it so that there are less places where collisions can happen. So if there's less places for collisions, that means that we're going to have fewer of them, and the reaction will be slower. Increasing the concentration means that I'm going to cram more particles into a certain size of space. So more particles means more collisions, and that will speed up the rate of reaction. If I increase the pressure, this is only going to matter for gases. So higher pressure for gases results from collisions of gas particles. So if I increase the pressure, I'm getting more collisions, which will also speed up the rate of reaction. Next question has an energy diagram. So what amount of activation energy is required for the reaction pictured, and how would a catalyst affect this reaction? So activation energy is the amount of energy that I need to absorb. It's the endothermic part of any reaction, and it's that energy that I have to absorb in order to break bonds. So whenever we look at the progress of a reaction, we can see that it starts out with a certain amount of energy, and it increases to the top of the hill. So activation energy is from the reactants to the top of the hill. So if we wanted to find a numerical value for this, we would see the top of the hill is at 80 kilojoules per mole, and the reactants are at 60 kilojoules per mole. So whenever I find the difference, I see that I have to absorb 20 kilojoules per mole of activation energy. The addition of a catalyst is going to make that hill a little bit smaller. So instead of it being at 80, maybe it's at 70 or 65 kilojoules per mole. So this will lower the required amount of activation energy, which will allow this reaction to take place at a faster rate. So basically that little drop in the hill is the effect of the catalyst. Next question, we have a reaction, and we want to look at what's going to happen whenever we're at equilibrium. So let's compare the rate of the reaction. So whenever we get at equilibrium, the rate of the forward reaction is equal to the rate of the reverse action. So it's kind of like you're digging a hole and your friend is filling the hole. If you are digging just as quickly as your friend is filling, the hole doesn't change. So that's how we know that we're at equilibrium. So the rates are going to be equal for forward and reverse reactions. Compare the concentration of A, B, and C when at equilibrium. So when at equilibrium, by definition, our equilibrium constant is equal to 1. So there's our equilibrium constant expression. The only way that that fraction can equal 1 is if the top and bottom are the same numbers. So in other words, the concentration of C is equal to whatever the product of the concentration A times B is. So the amount of reactants and the amount of products aren't necessarily going to be the same, but it does mean that the ratio of them equals 1. Next question is about Le Chatelier's principle. Indicate the direction of the shift for the reaction. So if we look at removing water, anytime you remove something, equilibrium is going to shift towards it to replace what we've lost. So the idea here is that we're trying to keep that KEQ, that constant, we want to keep it the same. And the way we do that is by altering the concentration of my reactants and products. So if I remove water, I'm going to shift towards products in order to regenerate, to replace the lost water that we've taken out. Adding energy. So if you add something, we have to move away from it to use it up. So I'm going to shift towards my reactants, shifting away from energy, which is a product, so that I use it up. Lastly, reducing the pressure. So pressure only matters whenever we're talking about gases. And here we've got hydrogen, a gas, and oxygen, a gas, reacting to make water vapor, also a gas. So whenever we reduce the pressure, the system is going to try to respond in a way that's going to bring the pressure back up. So it does that by shifting to the side with more moles of gas. So if you have more moles of gas, there'll be more gas pressure. So we're going to shift towards the reactants because that side has 3 moles of gas, 2 moles of hydrogen, 1 of oxygen, and the product side only has 2 moles. So we need to shift towards reactants because there's more moles of gas there. Next question has us completing some nuclear reactions and then labeling them as fission or fusion. So we have to remember that the mass numbers need to sum up on both sides to the same number, and our atomic numbers need to sum up to the same number on bottom. So I need to have a total of 226 for my first equation here, and I've got 1 alpha particle. So that means that I'm going to have this particle with a mass number of 222 and an atomic number of 86, so that everything adds up to what we have on our reactant side. The next one, we are starting with hydrogen and we are making a helium. So that means that I need 2 hydrogens in order to do that. So this is what the sun does, fuses together hydrogen to make helium, other nuclei as well. Last one, I'm starting with some uranium. And I've got a 92 on bottom, so that tells me I need a 90 on the other side because that adds up to 92, and 231 on top because that adds to 235. Fission is occurring anytime that a heavy nuclei breaks into a lighter nuclei. So think of the word fissure, which means like a crack in the ground after an earthquake. So that's something splitting apart. Fusion sounds like the word fuse, means 2 lighter nuclei are going to fuse together, join together to make heavier ones. So my first one is fission because I'm starting with a heavy element and I end up with 2 lighter products. Next one is fusion. I'm starting with 2 light hydrogen nuclei and they are fusing together into a helium nuclei. And my last one is also fission because I'm starting with a big heavy uranium atom, which is being split apart into smaller nuclei. Question 7 involves some half-life calculations. Carbon-14 has a half-life of 5,700 years and decays to produce nitrogen-14. So that means that if I had some carbon-14 and I sat there and watched it for 5,700 years, I would see that half of my carbon-14 had become nitrogen-14. So if I start off with 100 grams of carbon-14, how much nitrogen-14 will exist after 17,100 years? So first thing I need to do is figure out how many half-lives have passed in that 17,100 years. So 1 half-life is 5,700 years, which means that in this amount of time, 3 half-lives have passed. So I started with 100 grams of carbon-14. After one half-life, I've got 50 grams of carbon-14. The other 50 grams have decayed into nitrogen-14. Another half-life goes by, and I've only got 25 grams of carbon-14. And finally, after the last half-life, I only have 12.5 grams of carbon-14. The rest of that 100 grams, has decayed into nitrogen-14. So of the original 100 grams of carbon-14, 12.5 grams of carbon-14 remain, and 87.5 grams have decayed into nitrogen-14. If a sample contains 25 grams of carbon-14 and 175 grams of nitrogen-14, how many half-lives has it undergone? So the sample began as a total of 200 grams of carbon-14. So what I'm really asking you is how many half-lives does it take until only 25 grams of the carbon-14 remain? So if I have 200 grams and it undergoes one half-life, that's going to be 100 grams left. And then another half-life leaves me with 50. And then a third half-life leaves me with 25 grams of carbon-14. So that means that the sample has undergone 3 half-lives. Next question is about isotope notation. How would you find the number of neutrons for the isotope below? How would you find the number of protons? So, A represents the mass number, which is the sum of protons plus neutrons. Z is the atomic number, which is just the number of protons. X just represents the element symbol, so that could be a C for carbon or N nitrogen, or U for uranium, any element. So if I want to find the number of neutrons, I got to take the mass number and subtract out the atomic number. So I take the sum of protons and neutrons and subtract out the protons, and what I'm left with is nitrogen. To find the number of protons, we simply use the atomic number. Next question is about how to use nuclear reactions to generate electricity in a nuclear power plant. So this diagram here shows a simplified view of how a nuclear power plant works. So in my reactor, there are fuel rods which contain uranium or some other radioactive element, and the nuclear reaction is occurring inside. We have control rods. These are neutron absorbers, so they absorb excess neutrons to slow down our nuclear reaction. So I can insert the control rods further to slow things down or pull them out to speed things up, depending on what the demand is for electricity. So the nuclear reaction is going to generate a lot of heat, and that heat is going to be used to change liquid water into steam. So that heat is changing liquid water into steam in a steam generator, and that steam is going to go through a steam turbine, and that is going to generate electricity. So that output can then be used in a city or used to help run the plant, can be used as electricity. Then, once the steam has gone through the steam turbine, it needs to be recondensed into water so that it can once again absorb the energy of the nuclear reactions. So that's usually done by connecting the coolant system to a body of water. So cool water comes in, heat transfer occurs, the steam condenses back into a liquid, and then the cycle can be done again using the heat from the nuclear reaction.